I don't want to talk a lot about the test because obviously some people still haven't taken it, but you did a good job overall. I mean, there were some really good scores. Nobody was perfect, but some awful close to perfect. So that's good. Now, this is what you need to know, and I wish the other folks were here. Well, they're going to hear it on the video, hopefully, if they watch the video, which they should. Chapter 5 starts some of the most difficult stuff that we do in Algebra 2. Chapter 5 and Chapter 6, if you ask past students, typically that's what they'll tell you. These were the hardest chapters in the book. And it's not necessarily because there is really difficult stuff. It's because there's lots of stuff. You know, it's the remembering what to do for what that really drives people crazy. So what we're going to do is we're going to slow down here a little bit before Christmas break. And we're actually going to take 3 days on 5-1 and 3 days on 5-2. And then we'll have a couple of review days, and we'll have a test for you. Wednesday is the 21st. Well, that's November. That's not really helpful. Yep, Wednesday the 21st. I know you probably have quite a few tests going on in other classes on the 22nd. Bless you. So the 21st is when we're going to have ours in here. And it'll only be on the first 2 sections because there's quite a lot of material in those first 2 sections. And that way, when you come back after break, while you will need to remember some of that material as we go on to the new stuff, we're not going to technically be testing you on that so that you'll have to remember all of that over the holiday break. So, Chapter 5, when you look at it here, you see we're starting off right away, and it's very generic. It says polynomial functions. Poly means many. So we are going to be looking at algebraic equations that have many terms in them. You know, what happens and how do we know about them? And it ends up that after we get done with this chapter, if I put something like this up here, and my smartboard's not happy with me. Oh, please don't collapse. That would be bad. There we go. By the end of this chapter, you won't need to punch that into the calculator to tell me what that's going to look like. You will know. You know, you'll say to yourself, okay, I see that this is a degree 4 polynomial, which, yeah, right now doesn't mean a whole lot to you. And it has some stuff behind it, so it's probably going to look something like that. And you'll be able to describe to me the behavior as this goes to the left and goes to the right of this graph. But we have to take that in little pieces. We have to put together, okay, how do I know that? Where do I get that information from? What numbers, what letters tell me that? All of that good information. So that's where we're going. And like it says, today we're going to talk about classifying polynomials. Classifying in math means naming. We're going to figure out ways to name our polynomials. The one I had up there would be called a quartic. And we're going to talk about how we're going to graph polynomial functions and describe end behavior. And most of the time, when we get past our quadratics, we're just going to say, let's use the graphing calculator to graph these. So then you might say to yourself, well, why then do I need to know what the thing is going to look like? I punch in stuff on it all the time. I get going too fast, my big fingers hit the wrong key, you know, it happens to all of us. So you need to know whether or not that calculator is giving you the right stuff, or if you've made a mistake when you've punched it in. So we're going to start with these objectives here, which are just classifying polynomials, graph them, talk about some of the behaviors, all of that good stuff. So little getting ready here says this. It says the first column shows a sequence of numbers. And we take a look, bless you, and those are kind of small. Can you even make those out in your packet? Maybe if I do that, that would be a little better. So we see a sequence of numbers up here, and that's -4, -6, 450, 156, and 346. And somebody says to us, I want you to build a polynomial that'll go through all these points. Huh? We need a place to start. So what we do is we use what are called differences, and differences mean subtraction. That's what difference is. So the first column shows a sequence of numbers. For first differences, subtract consecutive numbers in the sequence. So here's what they're saying. We could take -4 minus a -6, or we could take -6 minus a -4. As long as you do it the same way all the way through, it doesn't matter. So what they did was they took 346 minus 156 to get this one, 156 minus 50 to get this one, 50 minus 4 to get this one, 4 minus a -6 to get 10, -6 minus a -4 to get -2. Now, what do you want to happen? We want all of these numbers to show up as the exact same number every time. Now, that didn't happen. I mean, we can already see that up here. This is -2, -10, and 46. There's no way that's going to happen. So then you do it again, and you find the second differences. And if those aren't all the same, then you do it again. So let's finish up this little chart here and do some subtraction. And I'm going to start from the bottom up since that's how they did the subtraction. So 346 minus 156 is 190. 156 minus 50, I'm sure we didn't have to punch that in, that's 106. Well, like I said, we can see -2, 10, 46, 106, 190, that's not the same. They're not the same numbers. So then we take 190 minus 106, which is 84, but again, we don't want to do anything in our head this morning. We wouldn't have to. We can grab a calculator. That's 84. 106 minus 46. 46 minus 10. 10 minus a -2. I'll do 10 plus 2, which is 12. 12, 36, 60, 84. They're not the same. So we go one more time and say, well, 84 minus 60, that's 24. That's what we're looking for. So what does it mean? What it means is we cannot write this as an x to the first equation because the first difference didn't work. We didn't get the same number every time. We cannot write this as a x squared, power of 2, because those didn't come out the same. But we can write this as an x to the third equation. And it will work. It'll go through those points that they have up there. So it's just a series of subtraction to see, do we get the same thing? If we don't, then we go on to the next set and the next set. And we use whatever line we get. Like in this case, this was the third difference to determine what power our polynomial should have to make this work. So if the pattern suggested by third differences continues, what is the 8th number in the first column justify your reasoning? We don't need to do that. That's working backwards and saying, if you found this from subtraction, now work backwards and do the addition. What you're going to have to do in your homework is this, where you do the subtraction until you manage to get a column that has all of exactly the same thing. And then we'll know what polynomial we will need to use, what degree to make this work. So, yeah, here's where it's mad because there's so much stuff open. Come on, you can do it. Go to the next one, there it is. All right, so now, there's lots of writing on this page, isn't there? Grab a highlighter. If we want to know what's important, what do we need? Or maybe you'll just circle or that kind of stuff, but a highlighter would be good. Something that's going to show up on that purple, so maybe the orange one or something like that that'll pull that off of there. So we just saw that the differences in that one give us the power of a polynomial that we should write to make things work. But what we want to do is figure out a little more than that. What are these things going to look like? So a polynomial function has what are called distinguishable behaviors. That means from now on, we shouldn't just look at a polynomial and go, oh, a bunch of algebra. We should try to chunk it up into little pieces that tell us what's going to happen. We could use its algebraic forms to know things about the graph. Look at it a little bit differently. we can use the graph to know things about the algebraic form. And this is usually where we start off. You know, we'll start off by graphing a bunch of stuff and saying, oh, look, they all do this, you know. So as we go through this chapter, there are going to be times where we do that. We'll just, hey, let's all grab our graphing calculators and let's see what's so special about this. You know, why is this different? But some of the things, because math has been around for thousands of years, people have already discovered it. And we want to take advantage of that and just say, oh, look at that. Yeah, if you do a bunch of these, this is what happens. So a blank is a real number. A monomial. Mono meaning one. A monomial is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. Wow. A monomial. One term. One term. So it could be the number 7. That's one term. It could be negative 8x squared. That's one term. Notice how these are all part of a product. They're all multiplied together. So that's what makes it one term. So like it says, it could be a real number. Might just be a variable. X is a term. You know, each one of those is one term, and that's a monomial. But it could be the product of a real number and one or more variables, because we could slap a y behind this too, and it would still be a monomial. So how do you know a monomial? Well, you're going to see just one term. There's nothing being added or subtracted. There it is. It's a monomial. And notice, whole number exponents. Now that's part of being what's called a polynomial function. To be a polynomial function, you have to have whole number exponents, which is a good thing for us. Because what that means is, we're not going to see any fraction powers. We're not going to see any square root of 2 as a power. Nothing weird. It's going to be just normal numbers. In fact, not even negatives. It's just going to be whole number exponents. Then, the degree of a monomial tells us a lot about the graph. Degree of a monomial in one variable is the exponent of the variable. So, for my negative 8x squared, the degree would be 2. The degree would be 2. If my monomial is 7, it said the power of the variable. There isn't a variable there. So I have to think, okay, if there's no variable, what was the power of the variable that made it not there? 0. Because if it were a 1, it would be 7x to the first. So if it's not there, if my 7 is there, it's because it was 7x to the 0. And that's because raising something to the 0 power doesn't make any sense, right? So by definition, in order for all the rest of them to work, as mathematicians, they had to say anything to the 0 power is 1. And that's why that works. So if you punch in any number to the 0 power or any variable to the 0 power, you get 1. That's how it works. So that's the one weird one when we go through this. Just remember, anything to the 0 power is 1. This is 7 because that's a 7 to the first. It's there. We can see it. It's there one time. But x to the 0 stands for 1. Stands for 1. All right. So degree is important. A polynomial is a bunch of monomials strung together. That's what it is. So a polynomial is a monomial or a sum of monomials, because poly means many. Poly means many. So if we have 3x squared plus 7x minus 4. I look at that and I say that's not a monomial because it has more than one term. Terms are separated by addition. So there's 3 terms here. There's 3x squared, there's 7x, but the last term is not just 4. Because remember, they're separated by addition. So they must have added a negative 4. So these are each of the monomial terms that make up this polynomial because it has to be addition. Now that's going to be important because we're going to give these things names based on how many terms we see. So in the future, when we see this one and we say there's 1, 2, 3 terms, that's a trinomial because tri means 3 in that. You know, we're going to give it names based on what we see for those terms. The blank, the degree of a polynomial. Notice this is not monomial anymore. The degree of a polynomial in one variable is the greatest degree among its monomial terms. So to tell something about these graphs, we're going to look at them and we're going to say, okay, which one of these has the biggest power? In fact, most of the time, we're going to put them in standard form. So the highest power comes first, then we just go down a power and down a power and down a power. Because it turns out that first term tells us a lot about what the graph is going to look like. So if we can figure out where the highest power is, we're good to go. A polynomial with the variable x defines a polynomial function of x. The degree of the polynomial function is the same as the degree of the polynomial. Don't worry too much about that. We're going to talk about degree of a polynomial. We mean degree of a polynomial function. That's just how it works. So it's just a little vocab there. Don't let it mess you up. Don't think, hey, that's something brand new. All right, so here's what we're talking about. Say I give you that. 3x squared minus 7x to the third plus 4x to the fourth minus 8x plus 9. It should bother you that those are not in the right order. If it bother you, we need to fix it. So we're going to put it in standard form, which means we're going to put this 4x to the fourth first because that's the highest power. And then we naturally say, okay, well, where's the 3? Right here. Next one up should be a 2 power, so plus 3x squared. And then minus 8x plus 9. Oh, there's a lot going on here. I mean, that's a lot of x's, right? I can tell you with absolute certainty the approximate shape of this graph just by looking at that right there. I look at this and I say to myself, this is a degree 4 polynomial. If it has a 4 in the front, the fancy name for that 4 is the leading coefficient. The leading coefficient being a 4 is helpful, but even more helpful to me is that that 4 is positive. So knowing that there's a positive number in front of that helps me out. Here's what I can tell you about the graph just from that. I can tell you that the graph will be doing that on the left side and that on the right side. Absolutely will be doing that. Now what I don't know for sure without doing some more math is exactly what's going to happen in here. But looking at this, notice how there's a lot more x's over there? That tells me there's going to be some lumpy bumpies in the middle here. But somehow this is going to do a little bit of a wavy thing. Probably not that many. Might do something like that. Well, let's see. Check it out. What does this really look like? 4x to the fourth minus 7x to the third plus 3x squared minus 8x plus 9. And we'll probably have to change our window because I just made this up. So yeah, we're not seeing all of it. So let me get some more y's on here. Let's see. So what's happening here is it's kind of coming down and then slowing down a bit and then going back up. But do you see how those initial two arrows I had up there are absolutely true? That's called end behavior. And that's a part of what we're going to learn about in these first two sections, is end behavior. And that all comes from this, right here, from that term. Okay, Cedar, so how do you know that? I mean, what if it's 4x to the 78th? Well, x to the 78th is going to behave just like this one does, because it's an even power. So here's what I need you to have down before we even go on to the other notes, so that everybody understands that this is not, I'm not waving a magic wand and know how these work. We have degree, and we have the leading coefficient. We're going to do this in a little chart type of thing here. So you get that first term when they're in standard form. And you look at the degree, and you see that your degree is even. So you look at that power on that highest number of a power, and your leading coefficient happens to be positive, it will be parabolic. The overall shape of the graph will be parabolic. Whenever this is an even degree and the leading coefficient is positive, it's going to look something like that. Now, like I told you, in this middle section right here, there could be some lumpy bumps, some turning points is the math name for them. But that absolutely, we will see those two arrows going up every single time. It doesn't matter if it's x to the second or x to the 84th. It doesn't. Now, if our leading coefficient is negative, you guys know what's going to happen. If it's a negative x squared, what did we see? It went down. Again, stuff in the middle, we might see some turning points, some wavy stuff, but we absolutely know that it's going to go down and down. That's what it does. Now, we haven't had as much experience yet with the odd. That's what this particular chapter is about, looking at all of them. So when we have a positive leading coefficient and the degree is odd, we get a snake-like curve, an S curve. That looks like that. When we have a negative leading coefficient, it reflects it over the y-axis. Remember, over here with even degree, it flipped it down. This is going to flip it to the left. Doesn't matter if it's x to the third or x to the 57th. Again, the stuff in the middle might be some turning points, might be some lumpy bump stuff that we see in there. But where these arrows are going, called end behavior, that stays the same no matter what. It always does. So it's not some huge secret in math about how these things look. It's just looking in the right places, finding what you need. So it's all about that highest power and what's in front of that highest power term that will give you this information. So this says, key concept. You big stuff here. The standard form of a polynomial function is when we arrange these from highest power to lowest power. We don't just do that because we want to, because math people are into order. It's because then that first term becomes front and center. You see it right away and you can tell what's going on with your function. So this is kind of scary looking right here. But what they're saying is put your highest power here, then subtract 1 and put the next one here, then subtract 1 and put the next one here. And yes, there are going to be some numbers in front of it, a sub n, a sub n minus 1. But it's exactly what we've been doing. We've got 4x cubed plus 3x squared plus 5x minus 2. That's not scary. We can order those. That's standard form. Now we look at this and see, hey, this is odd and this is positive. And that's the sketch that should come into our brain right away. Going to do something like that. Now, this X business in the middle, probably going to make some lumpy bumps in the middle there. But I know this graph is going to go down over here and it's going to go up over here, just based on that first term. So, naming them. We're going to talk about them. If we're going to talk about them, we have to have names for stuff. So a polynomial can be classified or named in two different ways. The first one would be by its degree. And remember, the degree is that highest power. And the second is going to be the number of terms. And remember, those are separated by addition. Oh, it's mad. It doesn't want to write the rest of that. There we go. All right. So, if it has a 0 degree, it is called a constant. And that's what Emmanuel was talking about earlier. It's the confusing one where you look at it and you go, well, there aren't any x's because it's x to the 0. So it's just a number. Example would be 5. And it's x to the 0 because the x isn't even showing up. So that's why it has a degree 0. Now, there's only a 5 there, so pretty obviously that's one term. And one term, monomial. Mono meaning 1. So 2 names for 5, for goodness sake. You see a 5 on a piece of paper, classify it. It's a constant, and it's a monomial, depending on whether or not you're looking at the degree or the number of terms. This little bugger, that's an x to the first. That's why we see it. So x to the first plus 4. Well, anything that's x to the first, that's going to be linear. That graph is a line. So x to the first is always linear. X to the 0 is constant. X to the first is linear. We look at it and we see, okay, they're separated by addition. There's an x and there's a 4. There are 2 terms here. 2 terms, binomial. Bi means 2. Next one up, 4x squared. Well, the power that we see there is a 2. That gives us our parabolas. The parabolas have a fancy name, of course, when we're talking math, and that's quadratic. So those are quadratics. If you have a degree 2 polynomial, you are looking at a quadratic. But this little bugger, 4x squared, that's just one term, so that's still a monomial. It's going to be about, what do we see for degree? And we can give it a name by degree, and then what do we see for the number of terms? We can give it a name by the number of terms. All right, this little bugger here has a 3 for its degree. That's called a cubic. So those are cubics. When we see degree 3 polynomials, highest power of the variable is a 3. But it does have 3 terms. It has 4x cubed, negative 2x squared, and plus x. So that's a trinomial. And that's vocabulary I've used all the way through when we were factoring. I'd say we've got to take this perfect square trinomial and we have to make it a binomial square. So now we're putting that together and it makes sense. 2x to the 4th plus 5x squared. Okay, the degree is 4. But somebody threw this out of whack. I always think somebody was trying to be a big joker. Because in math, 4 is generally quad. Somebody put that up here for 2. They came up with it first and they thought, let's just mess up the whole system. But we call it a quartic. A quartic. Kind of think of it like quarter. Quartic. 4 quarters in $1. But this little baby only has 2 terms. 2x to the 4th plus 5x squared. So what name do we give it because of its number of terms? Binomial, exactly. Still just 2 terms. Last one. Negative x to the 5th plus 4x squared plus 2x plus 1. The degree is 5, and that one is called a quintic. I think it always comes back to me if you read any Sherlock Holmes or mystery, things like that from way back in England. You know, they'll talk about a quince and those type of things that were worth 5 of whatever it was they had for their monetary system. And then there are 1, 2, 3, 4 terms. Monomial is 1, binomial is 2, trinomial is 3. What do we do for 4? Well, actually, after that, we just call them polynomial of blank terms. So this is a polynomial of 4 terms. Because polynomial, poly means many. So we just say it's a polynomial of 4 terms. There are fancy math names for them out there somewhere. But really, the ones that we need to know are the monomial, binomial, and trinomial. And we get those pieces. There are also fancy names for 6th degree, 7th degree, 8th degree, and all that good stuff. But rarely in here do we even get to see the quintic stuff. You know, usually it's going to be lower than that. So now, we are just naming. That's all we're doing. Write each polynomial in standard form. Okay, that means highest power first. So 9x squared plus 3x plus 5, because I have to do the x to the second, then the x to the first, and then the constant. Now, classify it by degree. So what's the highest power? A 2. And what was the fancy name for powers of 2, degrees of 2 in our little chart? Quadratic. So this is a quadratic. How many terms does it have? So it's called a trinomial. There you go. Oh, so that. Oh, look at B. What's the highest power in B? 4th? All right, so we're going to start with that and work our way down. Oh, no x to the 3rds. We need to put those 2x squareds together. Negative 6x squared plus 10x squared is plus 4x squared. And then we have a plus 4x and a minus 12. And how do we know it's a plus 4x in the front there? Because you look at that, you go, there's no plus. Well, if there's no minus, it's positive. Alrighty, what's the fancy name for the degree of this one? Quartic, degree 4. What name do we give it based on its number of terms? Yeah, polynomial of 4 terms. Like I said, I know there are fancy names for that out there somewhere, but we're not going to worry about that. Alrighty, got it 1A, same directions. Write it in standard form and then classify it. Is A already in standard form? No. Give me the name by degree. Quartic. Name by number of terms. Already heard some people whispering it. Trinomial. Is B already in standard form? No. Alright, so let's see. Negative 4x to the 5th. We don't have any x to the 4th, we don't have any x cubes, but we do get a 2x squared. And then we see, oh, there's 2 numbers we can put together there, 3 and a 10. Name of this thing by degree.
Quintic.
And yep, 3 terms. Trinomial. That won't be such a bad part of the assignment, will it? So, get it standard. Well, yeah, there's other parts. So, we're naming it, classifying it as naming it. All right, now, as it says, if you're given a set of polynomial function outputs and the inputs differ by a constant, that's what I don't like about that getting ready that we did today. You remember the columns before? They only gave you the outputs. When you're checking to see these differences that they want us to test for, you have to see that all the x's go up by the same amount. They can't go 1, 3, 7, 14. They can't do that. It has to be 1, 2, 3, 4, 5, or 4, 5, 6, 7, 8, or even 5, 10, 15, 20. Those intervals need to be the same. And then we can determine the least degree of a polynomial function that would give us those numbers by doing those differences, by doing some subtraction. If the first difference is constant, notice the word first, which would be a 1, well, then we'd use a degree 1 polynomial. Linear ones. We'd use a degree 1 polynomial. We'd use a line. So we do all the subtraction and bam, right away, there it is. We can see they're all the same number. We're going to use a linear model. Second differences, not the first. You already did the first ones, they didn't work. What's going to be the name of that one? Quadratic. So it's not a guessing game about what model you should use. You know, there's math to show us that stuff. And then if it takes the third differences, well, then you're going to have to use a cubic. If it takes the fourth differences, you'd have to use a quartic, etc. So this all ties in with those names that we were using. An example for problem 4 says we're going to use differences to see what should we use for this one. If we want a model for this, what should we use? Now, here's the first thing to check. Do those x's go up by the exact same amount every time? Going up by what? 1. You have to check that. If that's not true, then you can't do the rest of the math. You have to make sure it's going up the same amount every time. So now, we're going to do the subtraction. And like I said, it doesn't matter if we do it from top to bottom or bottom to top. So I'm going to do this from bottom or top to bottom this time instead of the reverse. It just is kind of natural. So -1 minus a -7, well, that would be -1 plus 7. And that's 6. -7 minus a -3, that'd be -7 plus 3, and that's -4. -3 minus 5, -8. 5 minus 11, -6. 11 minus 9 is 2. 9 minus a -7 will be 9 plus 7, which is 16. Any chance we're going to be able to write this with an x to the first? These are not the same. So this was our first difference, and it didn't work. Keep going. Now it's important we did that math right, because obviously things will get thrown off if we don't do the subtraction right. So some of you, I'm sure, were thinking, why grab a calculator to do that? Then grab a calculator. You know, it's perfectly fine. All right, so we're going to try a second difference. 6 minus a -4 would be 6 plus 4, which is 10. -4 minus a -8 would be -4 plus 8, which is 4. We can already tell it's not going to be a second difference, but we need to get the numbers so we can keep going. -8 minus a -6 would be -8 plus 6, which is -2. -6 minus 2 will give us -8. 2 minus 16, -14. Not going to be able to write this one on the next square with the quadratic. So let's keep going. Now Now we're trying third difference. 10 minus 4, 6. 4 minus a negative 2. Hey, wait a minute, that's 4 plus 2, that's 6. Oh, let's keep going and see. Negative 2 minus a negative 8 would be negative 2 plus 8. Oh, it's looking good. Negative 8 minus negative 14 would be negative 8 plus 14, which is 6. So what's the name of the model that we would use for this? Degree 3 cubic. We would use a cubic, absolutely, model this piece. All right. On that differences thing, I know we're getting short on time here. Do you need another one? 43210, me. How do you feel about the subtraction to figure out the name of the model? Okay, I did see a couple lower numbers, so we'll go ahead and do this one. This one says, what is an example of a polynomial function whose fifth differences are constant, but whose fourth differences are not constant? So don't use this one yet. If we come up with one that says, hey, your fourth differences didn't work, but your fifth differences did, what would it be named? It would be quintic. So they're saying just make up a polynomial function that's a quintic. 5x to the fifth. All it has to have is the fifth power. So we could actually just put x to the fifth. That would be it too. That might be a little less confusing when you look at your notes later. What's with all the fives? Right there. That's a quintic. All right. Let's check out this bad boy. A little bigger numbers. Negative 3, negative 2, 1, 0, 1, 2, 3. It's all good. 23 minus a negative 16. That'd really be 23 plus 16. Negative 16 minus a negative 15 would be negative 16 plus 15, which is negative 1. Negative 15 minus a negative 10 would be negative 15 plus 10. Is negative 5. Negative 10 minus a negative 13 is negative 10 plus 13, which is 3. Negative 13 minus a negative 12 is negative 13 plus 12, negative 1. And negative 12 minus 29. Oops. So, are we going to be able to do this with an x to the first? Nope. Let's keep going. See if we'll work with x to the second. 39 minus a negative 1 is 39 plus 1, which is 40. Negative 1 minus a negative 5 is negative 1 plus 5, which is 4. No, second isn't going to work, is it? Negative 5 minus 3, negative 8. 3 minus a negative 1 is 3 plus 1, which is 4. Negative 1 minus a negative 40 is negative 1 plus 41, which is 40. Can't write it as a quadratic. 40 minus 4, 36. 4 minus a negative 8 is 4 plus 8. Negative 8 minus 4, negative 12. 4 minus 40, negative 36. We writing this as a cubic? No. 36 minus 12, 24. 12 minus a negative 12 is 12 plus 12. Ooh, 24. Negative 12 minus a negative 36 would be negative 12 plus 36. 24. What's the name of the model that we could use for this? Fourth difference? Quartic. Linear, quadratic, cubic, quartic. All by subtraction. Well, just by using subtraction to get those places. All right, now, what I went through with you earlier is talking about that end behavior of the graph. So, the degree of a polynomial function tells us whether or not it's going to be parabolic or if it's going to be that snake-like curve. It affects the shape of the graph, overall shape of the graph, and determines the maximum number of turning points or places where the graph will change direction. So just knowing, hey, this is a degree 3 polynomial with a positive number in front, that gives us tons of information about the graph. It also affects the end behavior, the directions of the graph. As you go to the left forever and as you go to the right forever, what's happening with this graph? For polynomial functions, there are 4 types of end behavior as you move to the left and move to the right away from the origin. Could be up and up, and that's our little sketch of the parabola. Could be down and down, so both of those are even degrees, one with a positive leading coefficient and one with a negative. It could be, as we read these off from left to right, down and up, and it could be up and down. Bless you. And that's all based on the degree and the leading coefficient. And they have the 4 sketches down here too. But now, what we have to do is use actual math notation. The back of your book is worthless for this because the back of your book says up and down and down, and it's no good. So here's what we have to do. We have to write a little bit of calculus notation, a little bit. LIM stands for limit. The limit as x approaches, and my negative got lost there, negative infinity of our graph. Here's what this says. As x goes to negative infinity, imagine that number line up here at the front of the room. Negative infinity, that away. As our graph goes to the left forever, where is it going? As we go to the left forever, so just looking at the left of this graph, where's that arrow saying that we're going to go? Up. And up is infinity. Then we talk about as it goes to the right forever. The limit as x goes to infinity of f of x equals. So negative infinity here for x was to the left. Infinity is to the right forever. So as this graph goes to the right forever, just look at the right side. Is that arrow going up or down? Up. That's infinity. So we're not going to write up and up. We're going to write this notation. Now what does that mean for you? You have to practice writing this. This piece we get from the graph. We look at it and say, if it's going up, we're going to put infinity. If it's going down, we're going to put negative infinity. And then know that up is positive infinity and down is negative infinity. So when you look at the back of the book, you'll know whether or not you're right or not. So those are the graphs. We are big time running out of time here. So know that you probably won't be able to do all of the homework. You're going to be able to get through a good portion of it, but not all of it. There we go. So go through and do your naming by degree and naming by number of terms. And then you'll probably have to stop and wait for Monday for us to talk more about this end behavior stuff. But go through and do everything you can, especially the review problems to do those. But like I said, we're going to take 3 days on this stuff. We're going to make sure you get it right the first time through. type 1, 3 days for type 2, couple of review days, and test on just 2 sections.
Wait, I like